It's really.
Hi, Moss. Hello.
Hi, hello. How are you?
Welcome. Pointed at Lorenzo.
Hello, Mas.
Moss.
Hello.
Nice
Lorenzo.
to see you. Thank you for being with us.
You're
Thank
welcome.
you very much.
Thank you.
Hello, I'm Eric. I'm one of the students from Franklin and Marshall working on the project. It's nice to
Hey.
meet you.
Yeah, nice to meet
Masa
you.
Haru Itagaki, one of our board members.
Nice to meet you. We're just getting things set up right now, and then we'll be started shortly.
Maybe I have to. Yes, we are now attending the other board members,
Yes,
and maybe from Ukraine. I think they will be
Ukraine.
there.
yes. And some of our end users are going to join.
Yes, yes. Maybe when I talk, it's nice to be with the background. Eric, are you recording? Yeah, because. Okay, that's very important. Okay, maybe it's fine because if you have two audio close, we have a feedback.
Yes.
Yes, I hear. Maybe. No.
Yeah, you need to have the volume all the way down too. Yeah, good.
Is it working?
Yes. On your phone, I see you, and then on
Good.
here, I'm recording your full body.
Do we have people
Let's set
joining?
up.
Is it populating?
Yes, it is
Great.
populating.
Oh. Hello, everyone.
Hello.
Hello, Lorenzo. How
Hi.
are you? Are you ready?
Yes, we are
for
ready.
meeting? Yes.
We are here, and so we are
Mhm.
waiting for the others from Ukraine. And
Yes, they are connected.
No, they
Hi,
can't see us.
Tatiana.
Hi, team. Hi.
roll up.
Very good. The weather is very
Kind of
nice in
official
Florence.
Yeah.
I can put this even lower. Sliding down this pole.
How many participants?
Hello, this is Frody Crawford on Zoom. Are you able to hear? I don't know how to make this.
Yes, we hear you.
Okay.
Не знаю, где-то там.
So this is going out to Lorenzo and company down in the garden. Are you able to hear?
Yes.
Yes.
Okay, thank
Yes.
you. And Okay, I'm trying to
Hi,
connect. with the-
Felicia.
You can hear. I'm trying to connect to the group down in the garden. I see Lorenzo on the
Hello.
camera.
Hello, Felicia.
Oh, I see the
Road
garden.
number-
Close all the other. apps, because
Yeah.
that's the-
Maybe
Just
Uh,
go.
I want to keep that one open because I'm going to be using that in just a moment. I want to keep that one open. Don't need that. God, I got tons of crap open here. Okay, that's better.
Can you hear my voice?
Yes,
Yes.
Yes, we can. hear you.
Yes, yes.
Wonderful.
Roni, can you see my
Is-
iPhone screen on my computer?
Yes, I see it.
Great.
Perfect.
I'm going to switch to Hedges and see if you can see the Face ID.
Yes, shall I share that screen?
Not yet.
Not yet. I'm
Okay.
gonna help it on the robot. Can you see the grass in front of Ugo?
I see, yes, I do see Ugo, and we see a little bit of grass. Yeah.
You see my hand?
I see your hand. Yeah, I see your hand on the iPhone. Yeah.
We're all set. Thanks, Roni.
Yep.
I was 3 minutes left.
What's that? 3 minutes late. Yeah.
Whenever you're ready.
Yes, okay.
I think we should start.
First of all, thank you to you all, the advisory board, NATO representative, all the partners of this project. The project is called multi-sensors operative robots for secondary explosive threat detection. So what we will see today is a demonstration of the several technologies we are going to use in our robot swarm. We will have a radar, we will have a LiDAR sensor for detecting surface signature of landmines. We will have also the tripwire demonstration and detector demonstration, plus other processes. So we will have a sequence of these demos. Some are live, recorded. So I hope you enjoy. And at the end of this session, we will have time to ask you questions, if you have questions or comments. So the first trial today is the detection of signature by a LiDAR. This robot is the one we have developed here in Florence and is one of the three that will be used later. So you can, now we have an assistant, Luca Bossi, University of Florence.
Right. And then
Can
Professor
Brony share the-
Crawford, can you please share this screen?
See. LiDAR and photogrammetric image of the land surface in front of the robot as it's moving down a lane. It's recording these and it's going to piece it all together into a single swath that depicts the topography and any optically obvious targets. We'll take a look at what it's recording in just a moment. The robot's now turning to come back along the next line, the next lane. It's surveying in sort of a Greek line pattern.
Okay.
All right. Thank you for sharing the screen. You can now stop sharing the screen, Professor Bechtel. Or Crawford. Thank you.
I'm gonna have them share it again in just a moment, but not quite yet.
Yes.
Okay. I'm going to. Okay, they can now reshare
All
the
right.
screen.
Professor Crawford, please share the screen again.
As the robot was traversing these lanes, it was probably hard to see some things in real time. But one of the things that it just drove over was a simulant PMA2 landmine. This is one that our research group has been looking at for over 10 years now. It's a very difficult target because it has minimum metal, almost no metal, so it doesn't respond to a metal detector. And we've tried to image it with the holographic subsurface radar that you'll be seeing in a minute. And it's plastic. The dielectric properties of this mine seem to match relatively dry soils very well, so it's transparent to radar. So we've struggled with ways to detect this mine for quite a long time now. I'm going to go to some LiDAR images now. And we'll look at those. Oh, now you see me. The LiDAR is looking at me, but you don't want to see me. We want to look at, this is an optical image of the lane that the robot just drove. And it might look like a nice grassy lawn in Firenze, and in fact it is. But let me zoom in on this part of the lane. And those of you who are familiar and may have sharp eyes, you can see that on this testbed lane, we have a PMA2 landmine. It wasn't visible in real time to the naked eye, but we can look at the LiDAR data that we've collected. First of all, this was a test from just a few days ago, and this is a LiDAR model of that PMA2 mine in which the optical image has been draped across it. So you can see the landscape, you can see the topography, and you can see the mine. But now this is an interesting thing that we've discovered just in the last few days. Let's look at that same image, but just in the LiDAR and photogrammetry. And of course, you can see the landscape and the mine, but notice that super distinctive, we've been calling it a starfish, but it has 6 legs, so we should probably call it a spider. You can see that trigger, that 6-legged spider, very clearly on the LiDAR/photogrammetry. What's amazing is the diameter of this thing is about the size of a US penny or a dime. But if I zoom in, the resolution of the photogrammetry/LiDAR is so good that on that spider that has a diameter of about a penny, there are hundreds of polygons defining it. So we think we have terrific resolution. Now, of course, this is one sitting on the surface, and that's not what we're really after here. Let's go back to this. You see how they're typically buried with just the spider sticking up. So we did some LiDAR testing of exactly that. And let's look at, here's an image of a PMA2 in the test bed here in Florence. And notice all the green things. They're the same color green as the casing for the PMA2. There is a spider for a PMA2. It's not optically visible at all, but if we go to the photogrammetry LiDAR DEM and look down on that, does anybody see a spider? There it is.
There it is.
It's hidden in the foliage optically, but we have sufficient resolution that even though it's just sticking up minimally above the leaf litter, we can see it. So we think this is one of the most exciting things that we've discovered this week. We've found a way to find deployed PMA2 mines that we have not been able to do before. This is a brand new capability for us. So
thank you very much, Team Bechtel. And as Tim Bechtel said, there are some landmines that can be triggered by thin wires. Could be metal wires, could be plastic polymeric wire, like fishing line. And so another activity that I would show you is the detection of tripwires by high resolution camera. This is a setup here in Florence, organized by the Franklin and Marshall team. You hardly see, probably from this video, the very thin, transparent fishing line. But of course, if you have an optical system with enough resolution, you can detect this according to some processing. And so I will leave now the microphone to our colleagues that are in the control room inside the building, where you will see some results about the detection of tripwire.
Hello, everyone. My name is Ethan Senatora. I'm a student at Franklin and Marshall. I'm going into my third year.
Yeah, hello everyone. I'm Yihao Zhang. I'm going in my senior year. I'm working on the tripwire detection as well.
Yeah. So as Lorenzo mentioned and Professor Becto mentioned, we've been working on the tripwire detection, and we've been able to run some experimentation as well as develop some program to detect the tripwires. We can share a screen now to show you the images of previous or before the processing occurs, and then after, and what we've had as a result. So on your screen, you can see one of the images of the tripwire. Essentially, what ends up happening is that we are using the 0.1 millimeter thick fish wire, which is the most difficult to detect compared to all types of tripwire used. The transparent properties of this wire make it slightly more difficult compared to a metal wire, where it would stand out in front of the foliage. So this is one of the images. I can show you one more, and then we'll go on to another one. And now, after the processing occurred, this is what we're able to see. So in this image, we can see the distinct red line of the detection of the tripwire after the image processing happened and after we ran it through the code. In another image, we can see another distinct red line that essentially what ended up happening on this side of the image is that the light and the strength of the light was too strong and essentially removed the tripwire because it was transparent. Similarly, in the next image, it does the same exact thing, but a tripwire is being detected in both ways. I think this image probably highlights the code the best, simply due to the fact that you see a very clear red line that can be given to the operator, or at least the code.
And also for these two, we can detect them by setting our parameter to another level, and so that we can successfully detect these two, even we don't have the full line detected.
Yeah, and just to close off on one last thing, this aspect of the program is improving day by day, and then also we're learning more and more with the camera usage. So now we're just going to tinker with some settings with the camera to get the best results. Ideally, we can get in the image, we can see this result every single time. And yeah, that's it. Oh, and again, we would like to pass it off to Maxine and thank him as well for the tremendous amount of help he's given us with the development of this process.
Thank you to Ethan for the very clear explanation, but we have more interesting features for the processing of images in real time. And then we have now a presentation of the team in Kharkiv, Maxim Borodoba. Oh, sorry.
My Boroda, it's okay.
Yes, my Boroda. Sorry. He will explain his real-time processing demo to us. Please, Maxim.
Okay, I'll share screen right now up, but you're still able to see me. Up. Okay, I use some open source library to find and plot in rectangle line with different probability. In this small demo, I can show you like it's the process of this detection. I add some FPS score to like count how it's work pretty or not. And this is like raw image with the canny edge detection and hog line transformation. I add only some small post-processing, and I filter only horizontal line and the lines that has about 20 degrees angle. And now I can show you this like handmade picture. And as you can see, all lines that have about 20 degrees or less detected, and another one just pasted. So, okay. So as you see, it's for my low performance laptop and very low camera, about 0.3 megapixels. I can find some line in almost real time. So thank you for your attention.
Maxime. Thank you again. And I would like to say that the efforts of our partner from Ukraine has been really remarkable, because the difficult time they are living, and they are really contributing to this project remotely. Unfortunately, they cannot be here, but I'm sure that the situation will be better in short time. So I said at the beginning that we have another technology for the detection of metal contents into a landmine case. And so one of the robots that will be developed by the Jordan University of Science and Technology will be equipped with a metal detector. And we have done a mock-up here in Florence to see if it's possible to implement this technology. And so we have a recorded video from yesterday that will be presented by Munster Almomani from JAF.
Munster online, some trouble getting in. But I think
Good evening, all. I want
Are
to.
you ready?
Yeah, I'm ready. I want to share my screen. So at first, I just want to make sure, can you see this picture here?
Yes, we can see.
Okay. So I'm Inj Muntasir. I'm from Just University. So basically, my team and I have been working on the MD sensor and the mechanism and how we can integrate that to Jackal robot number 2. So basically, what you can see here is the top view of Jackal and the MD sensor and the arm. So basically, we have designed this manipulator to perform a mechanism or a kind of motion called the sweeping mechanism. So at first, the MD sensor will start scanning from right to left. And when the MD sensor just came tangent to any metallic object, the MD sensor can capture this signal, and this angle we call θ1 will be measured. At the same time, the MD sensor will go to left and start scanning again from left to right. So at the same process, we will have another angle called θ2. We will repeat this process for this edge and this edge. So eventually, we can have a 2D image of any metallic object buried underground. We have some animation here to show the process. So again, this is the Jackal, this is the sweeping arm. The red dish here is the MD sensor. Okay, so also we have this plastic shield here just in order to protect the MD sensor from any harmful sharp stones. Now, in order to capture this signal more accurately, we have another mechanism to the sweeping arm. So at first, the MD sensor will start scanning as we previously shown. After that, if the MD sensor just capture any signal, the whole MD sensor and the mechanism will go down, and the MD sensor will become like almost tangent to the ground, so that MD sensor can capture and detect the signal more accurately. We have some experimental work that have done. However, actually, we haven't yet designed the sweeping arm. So instead of that, we have this demo. Here we have the MD sensor and we have Jackal. So as you can see here, we have samples. So the MD sensor was able to detect these samples. This is sample number 2. Yeah, and that's it. Thank you all.
Montes here.
Yeah.
I did not hear any sound during the detection of the
Maybe, yes, Munster, thank you very much for showing the detection technology for robot number 2. Unfortunately, in your video, we couldn't hear the detection sound generated by the metal detector. But
Oh yeah,
of course,
I'm sorry
yes,
for that.
no problem, no problem. We know all technical problems to do this large and broad connection with different partners all over the world. So thank you very much to you, Professor Khaled, that coordinated the team and is also with us here in Florence. So now we can go to the next and the last demonstration of today, that is for the third robot. Then the third robot is equipped with a holographic subsurface radar that we call HSR, working at 2 gigahertz. And this radar is capable to find both metal and plastic landmines. So you see here in our garden, they have been buried several plastic and metal case landmines. And now our collaborator Luca Bossi from Florence will show you the scanning system that has been completely remotely controlled. And again, we are completing the detection with another technology. And all this information will be merged together, fused together to have a reliable detection in a completely remote way. The acquisition time is about 2 minutes, you see, and the area for catching information for a target is about 30 by 30 centimeters. You see the height of the antenna, the blue cylinder is enough to avoid the possible obstacles on the surface of the ground. The innovative part of this project is sorry, the design and the fabrication of a completely plastic antenna by 3D printing, like other components that have been shown before. So this project exploit very much the design of components with the 3D printed technology. Okay, so now the scan with the holographic reader is completed. The data have been transferred by Wi-Fi connection to a remote control unit. And now our colleague Luca Bossi will show the images that have been acquired and the processing we are applying to find a signature of a buried landmine. This landmine is a PMN1. You see here the marker we stick on the ground. And the mine is a plastic case one with about 11 centimeter diameter. So if our colleague is ready from the lab control unit.
Yes,
Maybe
Lorenzo. Good
yes,
morning.
please.
I show you the acquisition of a PMN1 landmine. This is the representative images recorded by the holographic radar. You can see at the top of this window the representation of amplitude and phase of the received signal. And at the bottom of this window, you can see the position of samples taken during the acquisition. In the center of the images, you can see easily an area with contrast that represent the position of the mine. This is the representation of raw data. If we can apply other algorithm to reconstruct the field, electromagnetic field at an arbitrary distance plane from the antenna plane, acquisition plane. And I show you how from these images is possible to focus better and recognize the shape of the PMN1 landmine. Just a moment. Okay. You can see here the hologram, the recorded hologram, and I have here a slide to move to focus planes parallel to acquisition plane far away from the antenna. Here you can see at the bottom the distance from the antenna, and going at about 7 centimeters, we can identify easily the circular shape of PMN1. Okay. Lorenzo, if you want to add other information.
No, thank you. You have done a fantastic demo showing that a plastic landmine can be detected by analysis of a microwave imaging acquired with holographic radar. So now I think we have completed the three sessions for the demonstration of the the remote sensing technologies that we are implementing on the three different robots. So I would say that in each robot we have some innovation part. We like to do also research, and we like to have the state-of-the-art technologies mounted on the robots. And the final project aim is to have a demonstration with the three robots that are programmed to cover a Greek line and a real field. And this will be, we hope, ready in about a year and a half. So before to leave space and time for possible questions and comments, I would like to again to thank all the teams that are here in presence, and also the Ukraine colleagues that have been really supporting with a lot of working on processing, of course, for the development of this very complex system. So thank you very much, and we are ready for comments or questions from all of you.
Question, please raise your hand on Zoom, and I will call you to ask your question.
Of course, so you can use also the chat for dedicated questions.
Lorenzo, may I ask a question? Why you decided to change Greek line scanning trajectory of holographic radar antenna to spiral one?
Yes, a very good question. Why the question is why we have decided to have a spiral path for the scanning. The answer is comparing to the previous solution that was a Greek line path. In this way, we don't need to decelerate quickly and accelerate quickly the head with the antenna, and so we save energy, electric energy, sorry, for the battery, and also we have less oscillations, mechanical.
Very good. Thank you very much. It's a very good solution.
Other questions? I cannot see now all participants, but I see I see 21 connections. Oh, hi Felicia, nice to see you.
Hi Lorenzo, I'm trying to find my hands up button, but can I make a comment anyway, since I just unmuted?
Please.
You've done a fantastic work and a really wonderful demonstration of the technologies that you've merged together. It's just really fascinating to see how things can be detected in near real time. Really made tremendous progress. One question that I do have is, and I know that this is something coming down the pike, but the antenna is so close to the ground and you must rely on a flat surface. Will there be any availability for a less flat surface for detection so that the antenna isn't hitting the ground, you know, almost like a cantilever?
Okay, thank you, Felicia, for the question that is a real problem in practical situation. Now we have used about 8 to 10 centimeter height of the antenna from the ground. That is the general height that has been used by manual operator to avoid any contact with the ground that possibly can trigger a landmine. We have achieved this height by designing the antenna that can work in a far field, so with a certain distance from the ground, keeping a good resolution. So we found a compromise, as always in engineering, between resolution, sensitivity, and so on. But of course, we have no chance to go closer in practical thing, in practical application, because the roughness and the trip wire presence and so on. That is a good question. We have also an additional information now, as Tim Bechtel showed before. By the LiDAR, we know exactly the minimum height between the antenna and the top object, the most closer object from the ground. So we can also estimate which is the minimum height between the gap, the air gap between the antenna and the soil. Is it clear?
Yes, absolutely.
If I could add, this is Tim. The other thing that we can do with the LiDAR data, we really have superb resolution of the relief on the soil, and that relief does affect the radar image. But since we have the relief with such precision, we can correct the image for that relief. So one of the things we need to do in the future, in the next year and a half, is precisely register the LiDAR relief image with the holographic subsurface radar image, and then we can get better, even better focus on the radar image.
It's fascinating.
Thank you, Tim. Thank you, Froni. I see in one spot the control room with Froni and Khaled. And again, I would like, of course, to thank my colleagues from JUST, Ukraine, IRE Institute in Kharkiv. JUST is from Jordan, and of course, Franklin and Marshall. But a special thanks and a special remarks to the students that we have here in Florence, and some are in other institutions, that are the real force, the real innovation in this project. They work together, even if they live in different countries. And now we know, for the COVID and the world now, how it was difficult to meet together and to work in present together. Besides this problem, they did a real fantastic work. Thank you again to our young researchers, young collaborators, and young students. Okay. If the other colleagues, they wish to give a final remarks before to end this session. No remarks. And so thank you again for participation, even from Japan, Masaharu, and all the others.
Thank you very much.
Thank you. Thank you very much for your participation. Bye-bye.
Thanks, Lorenzo. Thank all.